It gives me great pleasure this evening to introduce Professor Yang-Hui He, who is going to tell us about mathematical physics, the mathematics and physics, and Entangled Tango. But our speaker is a very distinguished, he has a very distinguished career behind him. He is now from the London Institute for Mathematical Sciences, but he did his undergraduate at Princeton University, where he did an AB, I think it was, which is, I presume, equivalent to a BSc. He went to Cambridge University for an MSc. Then he went to MIT for a PhD, where he did a PhD. So he likes to zigzag across the Atlantic. He went then to the University of Pennsylvania for a postdoc. From there he went to Oxford University, where he became a Fitzjames Fellow. He later joined Merton College, which I think he still has an affiliation, where he likes to do a little bit of teaching to keep his hand in train. And he joined the University of London and Nankai University before eventually joining the London Institute for Mathematical Sciences. This is a new institute set up in London, and it occupies the Faraday quarters of the Royal Institute. So they have very nice, luxurious premises there in occupying Faraday's quarters. He works on the interface of quantum field theory. Quantum field theory is our understanding of what we understand about nature is, in terms of quantum field theory, it incorporates quantum electrodynamics and the standard model of particle physics. The interface of quantum field theory, string theory, algebraic geometry, number theory, artificial intelligence and machine learning are his primary interests. So without further ado, let me hand you over to Professor Yang-Hui He. Thank you.
Thank you very much for that kind introduction. It's a great pleasure and honor to be here. I have a particular fondness for this island because my wife is from the north, somewhere near Belfast. So this is coming here. It's like almost coming home. I'm gonna, as Tango kindly said, I work on many interesting things in this fairly new institute, the London Institute, which is in some sense the English sister to DIAS, being an institute of pure research and no teaching. And we're very fortunate to occupy the old rooms of Michael Faraday. So it's a very interesting place, and I hope you guys can visit. And of course, I see young faces and friendly faces. So I'm very happy we see many young kids. So my job is to inspire you guys to do mathematics and physics. And I apologize, of course, to the experts who I have many friends in DIAS and in TCD and UCD, and I apologize to the experts that this is going to be far beneath their level. This is, and as I said, this is a very non-technical talk. These days I've been thinking a lot, and I have to, I'm working for my supper, because these days I've been thinking mainly about AI-guided discovery in mathematics, how AI can help us prove theorems and raise conjectures. Until my friend Sanjay invited me to give this talk about a subject I have not thought about for quite some time. So I'm going to beat him up after dinner. But for now, I will try to do my very best. And his invitation came quite timely, because there was just a few days before this, I was interviewed by the Nautilus magazine on this very topic, which is very beautifully written by Anono, the journalist, which is it's an extended essay about what am I going to talk about today. So in that sense, I at least have had a little bit of emotional preparation for what I'm about to talk, and then I will beat up Sanjay after dinner. So the talk is about the intricacies between mathematics and physics. So let's define our terms. what is mathematics? So mathematics comes from the Greek mathema, which simply means that which is learned or what one gets to know. I mean, that's a very interesting, right? It has nothing to do with what we now think of what mathematics is. And by the time of Pythagoras, around about the 6th century BC, the derivative word mathematikos essentially meant geometry and arithmetic, what we now think of mathematics. Right? So it's interesting that in this definition, that which is to be learned kind of gives the foundation of what mathematics is this thing as you try to get its axioms, you try to learn a method of attack, and you try to learn theorems from it. So this is, and of course, the first axiomatic development of mathematics is, of course, Euclid, right? Who laid down the axioms and foundations of what we now call this subject. So that's definition 1. Definition 2, physics. Now, this word came 2 centuries later, and it first appeared in Aristotle's lectures on nature, physical acroisis. And it's 8 books on nature. And this word physics first appears, this physiki, this word, is physics. And this physics is actually very interesting. This word in Greek simply means nature as in plants, the nature of things, the natural world around us. The natural world. And there's still a vestige of this. This great quote from King Lear in Shakespeare, take physic pomp, I love this word, take this line, take physic pomp, meaning take some natural herbs you pompous ass and try to cure yourself. And that retained this word physic. And indeed, as you can all the way up to early modern period, the word physic has nothing to do with what we now call physics. It simply means the natural world, herbs and plants. So the word that really had been throughout antiquity being used to describe what physics is really the word natural philosophy, right? So that's a much thing. The word physics to be used to describe natural philosophy came in the 20th century. This is a much, much later thing, or late Victorian period. So that's definition number 2. Definition number 3. As you can see, I'm at heart a mathematician. I need to define my terms before I can say anything. Science. The word comes from the Latin scientia, which simply means knowledge. Right? That's fair enough. I mean, that's what science is. I mean, it's knowledge. So mathematics is that which is to be learned. Physics in the natural world, and science simply means knowledge. And of course, every major ancient civilization has some kind of a notion of what science is. But of course, once again, we should go back to the Greeks, to Aristotle in particular, who used the Socratic method of debate on establishing the observation of nature to lead to experiment. And in that sense, that really began what we call science today. And the scientific method, which is, everything I think we're taught. I think in some sense, kids should be taught the scientific method. We know in school, we're taught science, go memorize this book. And that's completely not what science is about. And also, likewise, mathematics are taught in schools like, here's some formulae, go memorize it. That's completely not what mathematics is about, right? Mathematics is about certain exploration, and science is about exploration through this cycle. You formulate some hypotheses, so you experiment and you verify, you do observation, go back and forth. This cycle is now what we call the scientific method. And the key figures have contributed to the cycle. It goes back to Al-Haytham in the 11th century, and the Arabic scholar, and Ibn Sina, and all the way up to Roger Bacon in medieval Europe. Fine, so having defined our 3 terms, mathematics, physics, and science, the word science really, because I'm saying natural philosophy. The word science doesn't appear until the late the 14th century, and indeed the word scientist, which many of us are here, did not appear until 1833 in this famous letter that William Whewell from Trinity Cambridge, wrote to Michael Faraday. So this is quite interesting that as late as the 1800s, natural philosophers, the word scientist first appeared in that letter. That's kind of interesting fact. So back to what I was saying, we've defined mathematics, we've defined physics, we've defined science. One can clearly conclude that mathematics is not really a science. And it's very important to keep that in mind, right? Mathematics certainly does not, whatever mathematics is, in geometry and arithmetic, the derivation of ideas, of concepts, of theorems from axioms certainly do not, go through that cycle that I pointed earlier. Right, that, for somehow my slide is not showing that cycle, whatever it is. So David Eisenbart, who is the former director of the MSRI, the Mathematics Research Institute in Berkeley, he says it very well. And in many ways, mathematics is an art. In many ways, it is a science because he has the rigors of science. And in many ways, it's craftsmanship, this exploration of doing things. And by the way, this is a quote that I've taken from this famous video, which I highly encourage you guys to watch. It's a 3-minute and 33-second video on chalk. It's this particular brand of chalk called Hagoromo chalk, which all mathematicians around the world use. It's an obsession, it's a cult we have. And in the London Institute, we have boxes and boxes of this stuff. And in the Dublin, indeed, well, there we are. Thank you for pointing, I didn't know that. Oh, great, so it's the best chalk in the world. So if you guys want a chalk fix, this is what you get. Hagoromo. I should really get paid by Hagoromo company for doing this, but I just love it. It just writes so smoothly. Anyway, so this was in that 3-minute and 33-second video, which is incidentally the most watched video on YouTube about science, period. It has 30 million views. 30 million views is about chalk. Like, how did that happen? But in that sense, Professor Eisenbart defines mathematics in this very vague way, which I think is a very good description. So, okay, so it's like all of these things and more. So I still haven't given you quite a good definition of what mathematics is, or what mathematicians do. Well, perhaps the best way to describe it is this beautiful quote from Hardy, one of the greatest number theorists of the 20th century. So it's a very beautiful, I will let you read it yourself. In some sense, a mathematician's concern is about finding patterns, and that's it. Just like a poet finds patterns in language, or an artist finds patterns in a portraiture, a mathematician goes to find patterns in whatever, in however defined. A physicist supposedly finds patterns with nature, and that's quite different things. and this sense of beauty that Hardy was extremely fond of. This is from Hardy's Apology, Mathematician's Apology. Hardy, in this, he's obsessed with this idea of beautiful mathematics. Now that is something that I can't quite define for you. Right? There's almost a mystical sense of what beautiful mathematics is, and that defies definition. There is a human element in that definition. So here's a game that I try to play in trying to make this distinction between mathematics and natural philosophy. So you can think about this as physics if you wish, but noting that word, it was really Aristotle and then scientists until a much later 19th century. So if you think about some of the greatest figures that founded what we now today call mathematical physics. Right? I still, by the way, I haven't defined for you what mathematical physics is yet, but you can vaguely see where I'm getting at. So clearly, Plato, I would put him a little closer to the mathematics axis, simply because, it's hard to define these two. So Plato, of course, is interested in this ideal, right? This perfect world of ideals. So I think in that sense, Plato and the Platonic solids, the perfect solids, live in this world. Aristotle, of course, was really sort of introduced this idea of experimentation and extracting ideas from nature. And then Euclid, of course, is as mathematical as it gets. This guy laid the foundations of the definitions of the axioms of mathematics in 13 books of geometry and 5 axioms of planar geometry from which you can derive all facts that you know, that school kids are taught to memorize and should never be taught to do that, such as Pythagoras' theorem. You should be taught how to prove Pythagoras' theorem from the axioms of Euclid, otherwise it's completely pointless. I've kind of kept this vaguely chronological. Al-Khwarizmi, the great Arabic mathematician, from whose name we extract the word algorithm, and is the father of algebra. Right? Algebra, it's kind of interesting, it's very beautiful. Geometry, geometria, is a Greek word. Algebra is an Arabic word. It's the meeting of East and West, creating what we now call modern mathematics. So, and this is over here. So on this axis, clearly you have, Aristotle. Archimedes was interested in certain mathematical ideas, but Archimedes was very much a hands-on guy, having discovered things like buoyancy and thinking about these properties. And as I mentioned here, Ibn al-Haytham was really the originator of that cycle of the scientific method. I mean, it's really the first ideas of testing, observation. And Galileo, of course, later on, very much dropping balls from the towers of Pisa. Right? And then some Indian mathematicians. Here are some interesting ones. Aryabhata in the 5th century is somewhere close to this mathematics. I mean, he was solving quadratic equations, and yet he also thought about motion. Right? So somewhere over here. And Brahmagupta introduced zero. So that's very much mathematical. Now here are my 2 favorite figures. So now we're moving, so from antiquity we're moving towards modernity, and this is the early modern period. Newton, Leibniz, famously, the inventors of calculus. Now, interestingly, I mean, of course, there is a little bit of personal taste where you put these figures. I mean, this is a very rough plot, but Leibniz was thinking about zeros and ones and computation. Leibniz wasn't really thinking about the origins of motion or how do you invent something to a technique of mathematics to understand the motions of the planets. But Newton was, right? So in that sense, Newton was much more of a physicist than Leibniz. I'm very fond of Leibniz because he was my 13th generation grandfather academically. So unfortunately, I lay no claim to Newton. That's a different English line. But this is just by PhD. We like to think about it with some kind of continuity. Right? Newton is a very interesting case. Newton was clearly interested in motion. I mean, the Newton's laws, and he invented calculus to be able to understand that. Leibniz at almost exactly the same time did that as well, but without thinking so much about the origin of motion. For Leibniz, he was really thinking about this Cartesian world of tangents and whatnot. But I haven't put Newton here, but Newton I put right on this diagonal because he also did extremely important work in pure mathematics. He was classifying elliptic curves. He was one of the first people that classified what was something that I work on a daily basis, which is this number theory called elliptic curves. So Newton really was quite versatile scientist. So you can go on. So I've just named a few examples. Now, I encourage you for science-oriented people, go take your favorite hero and see where you can put on this plot. I think it's a very interesting plot. So back to this interaction, this dance between mathematics and physics. Galileo, as I said, even though I've put him on the physics axis, he was very much aware and quoted here in this famous essay that if you want to understand physics, if you want to understand natural philosophy, even if you want to understand experimentation, the right language to use is mathematics. For him, it's a linguistic issue. And this quote of Galileo resulted in an answer, and it's one of those beautiful answers. Oh, by the way, Galileo died the year that Newton was born. So if you're into reincarnation, is Newton was born in 1642, the year that Galileo died. And the answer to this, almost mystical quote is this book, which I think Tango mentioned earlier, the natural philosophy, the mathematical principles of natural philosophy, which I think is in the statutory thing. So I'm very excited to tell you about these words. So this is the word, the Philosophia Naturalis Principia Mathematicus, the mathematical principles of natural philosophy. This is an extremely important book. In 1687, printed actually not one block down from my office, because we have the Royal Institution and the old Royal Society was just right there. And this book was quite something that, a moment in human history. Because before 1690, I like to go very extreme. I tell little kids, in human civilization, there's pre-1684 and there's post-1684. The reason is because of the publication of this book. Why? It's because in this book, Newton answered this question in a very precise way. He was able to formulate his Newton's laws and then invent calculus, and then all of a sudden, humanity was able to explain things like the path of the comets and the tides of oceans and the circulation of the planets. It sounds very poetical, but that's a quote that's actually written on his enormous grave in Westminster in London, the size of this wall. And deservedly so. If you write a book like this, you deserve certainly a tomb that big. So, great answer to this mystical speculation of Galileo. And that book really started what we now call scientific positivism. This reductionist philosophy, and this is actually quite interesting, right? That the idea you can keep on reducing laws and you can write fundamental and increasingly fundamental equations until, after all, theoretical physics' point at some level is to be able to derive all phenomenon from some underlying equation. And that search, kind of kicked off in 1687 with that book. And I know here's a meme you can take. I don't know where. I don't know who did it. Is this from some movie? It could well be, right? I don't know if you can see. Yeah, see. But anyhow, so it's just this idea of increasing sniping is what we call scientific reductionism, right? That every single principle, just different levels of abstraction. Of course, this unfortunately has given many physicists a sense of arrogance, and I think this is just that is entirely it's unjustifiable. It just means that you're working at different levels of abstraction. There are plenty of problems mathematical problems in biology and chemistry and whatnot that are interesting in its own right. But this reductionist physics, in the sense of this book, is really carries on from this tradition here. So let me just, as an illustration, of this scientific positivism, this reduction. I won't bore you with Kepler's laws. I'm sure you remember them from school. But the point is, since the Babylonians, we've been looking up the star, looking up the night sky, and we've seen the passages of planets and whatnot, right? And so that's true. You can describe this to great precision. That's also fine. And Kepler, using the data of Tycho Brahe, was able to get this to such precise description that the path of the planets, assuming Copernicus's heliocentric view of the world of the universe, that they're elliptic orbits that have certain properties. So this is great. This is a beautiful piece of science that went for 2,000 years, at least 3,000 years. Right? The importance of 1687 was that the Principia Mathematica gave a completely paradigmatic change in the sense that you can just derive all of this really precise observations from these two equations. Now this, I'm not going to bore you with the derivation. It's about a couple of pages, and it's a standard first-year thing that you will see. And one needs to invent calculus to do this. That's kind of interesting that calculus wasn't ready but you needed to do this. So in that sense, this book answered a quest that went all the way from the Babylonians, the Chinese, and whatnot, all the way to be able to formulate this to explain the natural world, and it explained it perfectly, right? So finally, I can define two things, or at least give you a hint of these two definitions: the difference between mathematical physics and physical mathematics. So this idea of taking that observational data and then use the language of mathematics, and actually, given this two, you can really just detach yourself completely from any observation or from experiment, right? You're just using the mathematical principles of calculus, which even and differential equations and Cartesian polar coordinates to finally deduce that the solution of these two equations, the Newton's second law of motion and the inverse square law of gravitation that attract each other, can lead to, the solutions are the conic sections, which were known to Apollonius, to the Greeks. This is very interesting. It's a beautiful derivation. So that's mathematical physics, right? So you use a certain mathematical principles and use just the language of mathematics to derive something, and then you take this, you get this answer, and then you take this answer, you can actually check against Kepler's intricate data and see, oh wow, it fits perfectly. Right? When Newton was doing this, and Newton of course also experimented, but when Newton was doing this derivation, there was no reality involved, if you wish. It was just done in the language of mathematics. And that's very important to realize that. That's what theoretical physicists do. And that's why it gives us such heartwarming feeling when we do this. Right? It's just in the language of mathematics. Just like what Galileo had foreseen before Newton. So that's clearly, that's mathematical physics. I'm going to use the words mathematical physics and theoretical physics interchangeably. But then you can turn the question around. What is physical mathematics? Right? That's, hey, let's invent calculus along the way. I need this technique to be able to solve equations of such a type. Such a technique doesn't exist yet, so let me see what new mathematics I can develop. Right? Leibniz got to this point as well from a different angle, but mathematics is mathematics. So I like to make, you just bear in mind the contradistinction between these two. So I think I've defined all the terms, right? I've defined physics, mathematics, science, mathematical physics, and physical mathematics. And I hope, I haven't defined them rigorously enough, but I hope I've given you a flavor what any of these possible combinations mean. Right? Happy? A great quote from this one of the greatest theoretical physicists, mathematical physicists of the 20th century, Freeman Dyson, just to home in this idea that, for a physicist, mathematics is not just a tool, right? That it really is the source of concepts, right? So that you can somehow detach from reality and just do the calculation and then check reality. It's already quite different from other experimental branches, right? Where you're constantly checking against data. Here somehow with this abstract world of mathematics, you can ultimately detach and then reattach. It's very interesting that this is even possible, right? How is this even possible if you think about this from a philosophical point of view? I'm no philosopher, so I don't have an answer to that. But just want you to sit back and just question yourself. How is this even possible? Another great quote. I didn't expect this quote, but this is from Charles Darwin, who says, he became even more extreme that discoveries must be mathematical in nature. I didn't expect to hear this from Darwin, but then again, he's such a visionary, you can expect anything. So the take-home message somehow, when I say how is this even possible, it seems that the more fundamental inquiry is about our nature, the more precisely could be phrased in terms of and derived using pure mathematics. It's just a fact that we've learned from the last 3,000 years of investigation. Why? I have no idea. And I'm not alone in this. Far greater minds have asked exactly this question. So the Nobel Prize winner, Eugene Wigner, who was the founding father of the idea of using group theory in physics, the first person to introduce groups into physics, wrote this beautiful essay in 1959 called The Unreasonable Effectiveness of Mathematics in the Natural Sciences, which is essentially this question. Why is it that mathematics is so good at describing our world? So if you want to find an answer that I cannot provide, please go read this book. This essay. It's very short and very profound and very deep. Right, so. It gets even weirder. This line of inquiry sometimes even allows us to have theory before experiment. That's even more magical. When you have absolutely no experimental data to try to fit your model to, somehow in fundamental inquiry, sometimes the mathematics, and only the mathematics, guides us. And somehow, more often than not, you get the right answer. So let's have some examples. Before I do an example, here's a great quote from the great mathematician Hilbert, who realized by the turn of the 20th century. I mean, this is quite arrogant quote, but here's Hilbert. He can get away with saying anything. But just bear this quote in mind as I go through some examples. Right? The idea of by the way, this idea of doing no experiment, the thought experiment, when this is a word that's made famous by Einstein, the Gedanken experiment, he stole it from a much earlier Greek word, the diknoumi. The Greeks already knew this idea of doing experiments in your head. So let's take this example, which is very dear to my heart because the conversation about this happened in the very rooms that I work in every day. So Faraday was the greatest experimentalist of the modern times, right? But he didn't know any mathematics, right? He knew the physical principles of electricity and magnetism from the works of Coulomb, Ampère, and all these people. By the way, they're all French. Interesting, it shifted, right? The English school science shifted to the French because of the rise of Napoleon. And the Royal Institution was in fact established sort of as an answer to the rise of the French. But anyhow, I digress. And then he didn't know any mathematics. He was a brilliant intuitive experimentalist, right? And probably the greatest of all time in terms of just pure intuition. He was able to organize the set of then known principles about electricity and magnetism into certain things, but he couldn't really write them down until he invited Maxwell, who was a mathematician. And at the time, I'm not going to bore you with the details, he wrote down this set of equations. When they wrote this thing that I've circled in red was not there. Okay, so just cover your eyes. I tried to desperately edit on the plane to make this blurb out, but it didn't work. So you have to be imaginative. Imagine that this red circle were not there. Then you look at the set of equations, you can clearly see there's something wrong with it. It's not symmetric, right? There are two zeros here, there's something here, it's got a dot in it, it's got to be just, purely aesthetically, right? So this is just wrong. I think in that sense, Maxwell already felt that there's something wrong with the set of equations which is now known as the Maxwell equations. And they just simply said, wouldn't it be nice if I had this term there just to make it a little more symmetric? This is a very interesting way of doing science. There's no evidence, there's no experiment, it's just mathematical beauty. You would think it wouldn't work, right? Because why would nature obey such a PDE? And yet it did work because the theory came in 1865 that when they added this term is now called the Faraday-Maxwell term. Again, we teach this to our first years. But that's not good enough, right? You can say, well, this is just, math, you're beating yourself with some beautiful mathematics. And this term was measured within 40 years by Helmholtz. That's very interesting, right? This term was, this term was put there because it was beautiful. End of story. Of course, the actual story is a little more complicated. There's some intuition involved. This is exhibit number 1, right? Exhibit number 2, the famous story of Einstein taking the groundbreaking works of Riemann and Hilbert, pure mathematicians, when they formulated this idea of differential geometry based on the works of Gauss. That what happens if we're not working within the axioms of Euclid? That's a very interesting question, right? This has nothing to do with anything, right? Let's think about pure geometry with its 5 axioms of Euclid, and let's just bend it down, muck it around a bit, drop the 5th axiom, drop the parallel axiom, and that was something that was very fashionable between, say, 1820 to 1870. And finally, Gauss and Riemann were able to formulate a new branch of geometry. Nobody's really thought about what it has any implication whatsoever to the real world. And this thing on the left-hand side is curvature. It's a purely mathematical concept. And Einstein's genius was to realize, wait, this thing I can take and do Gedanken experiments and write something physical on the right-hand side. How is it? Well, you're Einstein for a reason, right? So the theory he did this in 1915, right? And very quickly it was verified by Eddington within 4 years. Because this new theory of gravitation that corrects Newton's, the one that I mentioned earlier, should bend light, right? And indeed, the Nobel-winning LIGO experiments about gravitational waves is very much in line of this. So this equation is not just 4, but a century ahead of its time in terms of predicting how nature should behave because of an underlying mathematical structure. Right? More examples. Paul Dirac was able to write down the Dirac equation, which we now call the Dirac equation. The theory he formulated in 1928. He wrote down the set of equations. Story goes like, it looks kind of interesting. I can't make one of the terms quite work out, but it kind of reminded me of this algebra that I kind of remember, something like Clifford algebra or something. And unfortunately, he couldn't go to the library because the libraries were locked. So he had to wait in the morning. He went there, and the rest is history. But the point is, with this Clifford algebra, again, a purely mathematical concept, he was able to predict the existence of the positron. There exists a positively charged particle that's just like the electron, has the same mass, except it has the opposite charge. Why? Why would you want to say something like that? Just because the Clifford algebra works out. And that was verified within 4 years. For which everybody got the Nobel Prize, everybody was happy. So this kind of thing happens over and over and over again in the history of science, that very often the beauty of the mathematics alone leads to profound insights about physics. Right? But of course, you have to test it. Right? Just because there are cases where there is beautiful mathematics that have led to nothing. But I won't tell you now, because I'll tell you that during our drinks, I'll tell you there are some examples. But it's interesting that there are more examples of this direction than there of the contrary direction. Why? I don't know. Makes a man religious. So if we plot, in fact, so there is clearly a divergence between theory and experiment in terms of time lag. Right? The more profound your theory is, the longer it takes for some experiment to finally verify. And that's no surprise, because the more deeply you dig into nature, even from a point of view of a size and scale, the experiments will get so intricate and so complicated, sometimes it takes 100 years before it could be verified. Right? This one, I love this one, where the Higgs boson was put in by Mr. Higgs and friends, because he made a beautiful scalar field that completed the Lagrangian stand model. Again, pure mathematics. And then 60 years later, it was measured, and that was the big sensation. Right? So where are we today in terms of this fundamental search for reductionist physics? We actually have done pretty well, from this framework of understanding the nature of space and time and particles. This is well known. There's the standard model quantum field theory is one. It describes the microscopic world of particles, and then there are experts here, and I will leave you to experts to explain more about such things. And the macroscopic world is described extremely well by this general relativity theory of Einstein, right, that I alluded to earlier. And we're talking about, this is the kind of precision that we're talking about in terms of experimental verification of the underlying mathematics, right? These are the most tested, the highest precision ever achieved in humanity for anything. 19 decimals precision. What I mean by that is like the theory, the masses and the couplings predicted by this theory agrees with experiment to 19 decimal places of measurement. Nothing else has ever achieved this. It's remarkable, right? And I play only with this. I'm usually kept very far from experiments just in case I jinx it. I tend to press random buttons and things blow up. So I was from a very young age, I was dragged away from anything that could possibly work. So at least I can just do this. Chalk on blackboard is fine. The worst thing can happen to you, the chalk breaks. But these are the two things that one explaining the world of the small extremely well, and one explaining the world of the large extremely well. And of course you have a natural question. Well, can I just put a plus sign and have an equation, a Lagrangian that would have the microscopic and macroscopic explaining both well? And that's a very natural thing to ask, and that is called the theory of everything. If you succeed in reconciling this with this, then you have a theory of quantum gravity. And that still is a challenge. So to understand the creation of the moment of the Big Bang, to understand the insides of black holes, you do need such a theory that reconciles these two. But we don't have such a theory yet. There is a great candidate, and string theory is one of the candidates. There are other candidates as well. I'm not here really to defend string theory. But what is interesting is that there have been, in the last 5 to 10 years, one after another, there's a sequence of books that have critiqued string theory, to the point that when I go to a pub now and I tell people that, oh yeah, I work on string theory, and it's like, but that's just wrong, right? I'm like, I don't have a clear answer to this. I'm not here to defend it either way, and I will explain a bit later. But let me just quote from one of the greatest theoretical physicists living theoretical physicist, Nathan Seiberg, at the IIS at Princeton. In terms of consistency and beauty and insights to both quantum field theory and gravity, no other candidate has come even remotely close to string theory. This self-consistency is extremely important. That's all I'm going to say. I can ask Nadi for further insight to this. So, yeah. One answer is this diagram, right? This divergence. People say, well, you've made no predictions that can possibly be experimentally tested. Well, just look where we're going, right? It's been 100 years since GR to this, and the next scale. How many I've made this? People tend to lose heart because of this, but But Dirac was an extremist. This is too extreme even for me. Dirac says, forget about experiment. I have mixed feelings about this. Some mornings I get up and say, absolutely, this is way to go. Some days I talk to a physicist, then I get beaten up. And then I'm saying, okay, maybe I should think a little more about this. But interestingly, Dirac, of course, this is, by the way, this is, Newton's great monument, the size of this wall in Westminster. There are 2 plaques underneath. This is very beautiful. One is Dirac, one is Hawking. So there's these two. These are the three, the sort of the mathematicians, the scientists' corner, mathematical physicists' corner in Westminster as a tribute to these great minds. So I'm not going to comment on this. You can take this message as you want. Whether you think Dirac is an extremist or just being sensible. That's mathematical physics, right? Now let's talk about physical mathematics, right? How am I doing on time? I can go on for days, but let me just check that I'm not going over time. Oh, I'm okay, good, right. So mathematical physics today has this problem, if you wish, or phenomenon of theory before experiment. Certainly when it comes down to the fundamental theory of everything, in terms of the reductionist theory of everything, there's that dilemma. When you turn it around, you get another interesting dilemma, and sometimes physics comes before mathematics. That's an interesting thing. How's that even possible? Right? I'm not answering anything. By the way, this lecture is completely pointless. You can just go home. I'm not answering any questions you may have carried with you. I'm just giving you more and more questions, but maybe that's what the point of the lecture is. So, the great Sir Michael Atiyah, and the great Robert Dijkgraaf, and the great Nigel Hitchens. Atiyah is one of the greatest mathematicians of all time, and certainly one of the greatest geometers of the 20th century. And Robert Dijkgraaf was the former director of the IIS at Princeton, and Nigel Hitchens is the civilian chair of geometry at Oxford. They wrote in 2010 an answer, well, I wouldn't say answer, a parallel to Eugene Wigner's paper that I alluded to earlier, the 1959 paper of Eugene Wigner. Remember going back here, when I went telling about this whole mystical feeling, why mathematics is so good at describing our universe. Right? These guys wrote a beautiful essay which turns this question around. It's called Geometry and Physics, but there's a line that says, the meaning of all of this is unclear, and one may be attempted to invert Wigner's comment and marvel at the unreasonable effectiveness of physics in mathematics. That's interesting. Physics very often goes ahead of the mathematics in trying to create new ideas. We've already seen an example of that happening. For example, the invention of calculus. By Newton, not by Leibniz. Leibniz got some other method, but Newton was able to invent calculus because he needed a method of dealing with infinitesimals to deal with motion. The intuition comes from the physical observation of the world, that is, or the natural philosophizing of the world, from which you can derive a completely abstract mathematical principle. Right? So this is a beautiful example of physical mathematics. And this is happening again, right now as we speak. And it's been happening since the 1960s and 1970s, when this remarriage of mathematics and physics have gone back. This does, that's why I call this this tango, right? Sometimes you go back and forth. It's hard to tell which one's ahead of its time. And this one is very close to my heart, and that's why I personally do string theory, because I no longer know whether string theory is a theory of everything. But what I do know for certain is that it's constantly giving new ideas in mathematics. Always giving new ideas, unthinkable new ideas in mathematics. I have no idea why that's even true. And that's just great. So I no longer, as a kid, I was like, one day I'm going to think about quantum gravity. I want to think about the theory of everything. And the older I get, the farther away I've moved that question, just because it's got too complicated for me to think. So I'm hiding away in my own little world of mathematics. I say, wait a minute, but this branch of physics is constantly solving new problems in mathematics in a strange way. Why is that? I don't know. It's like saying, let me phrase it this way. The majority of physicists, especially experimental physicists that I've talked to, says to me, oh yeah, I don't know, maybe string theory is right, maybe it's wrong. But every mathematician, especially algebraic geometers I've ever talked to, says, I cannot even think of a universe in which string theory is completely wrong. Because you guys are solving problems that we never even thought about, techniques we never even thought about. So let me give you an example of this. But before I do that, so as you know, in parallel to the divergence graph that I've drawn earlier about the theory preceding experiment, this time lag, just because the experiments are getting so much more complicated, so much more intricate. There is the other direction of physics and mathematics converging, right? If you think about, Einstein's theory of relativity and Riemann and the Riemann's formulation of differential geometry, that's a 60-year gap. And then Dirac's formulation of quantum field theory of the electron, and the idea that he got from the Clifford algebra, this lag is now gone down to 50. By the time we have gauge theories of Young and Mills in 1954, where they get the idea from topology, from Seifert, now it's gone down to 20. And we're at this crossroad right now, and that's why it's actually a very exciting time. Despite what you hear from the press, that, physics is dead, theoretical physics is dead, string theory is all wrong, we're actually at the most exciting time for theoretical physics and mathematical physics and physical mathematics. It's because we're at this crossroads. Witten is the first physicist to ever get the Fields Medal, which is the Nobel Prize for pure mathematics. He was able to use supersymmetry, clearly an idea from particle physics, to solve certain problems in topology and Morse theory. Likewise, the pure mathematician Richard Borcherds, who did get the Fields Medal, used an idea from conformal field theory and string theory known as vertex algebras in order to prove a conjecture in number theory and representation theory of groups. So that was in the 90s, and I think we're getting closer and closer. Now it's very difficult in our field to distinguish which is which now. So I think it's very exciting times rather than depressing times. So, by the way, so I tried to buy these books. So I've been babbling on about all this, right? So if you want to hear, so these are 3 editorials that I edited, containing the words of wisdom of the gods. Not my words. My words are useless. So in these 3 volumes, I try to get all of the Nobel Prize winners and all the Fields medalists that I can get my hands on, which is 6 or 7, to just let them have a dialogue and try to have this, where are we in mathematics and physics? But of course, the main motivation of me putting this shameless self-advertisements for these books is that because by them I get the 50-pound royalties per year, so I don't have to sell my liver for my children. But so C.N. Yang, by the way, is still alive. He's 102. If you think so, Penrose contributed to one of these books, or two of them in fact. Penrose is 92. He's like a young baby. C.N. Yang is 102. He's the oldest winning the oldest Nobel laureate alive, 102, and is still, kicking. And Penrose, of course, is unstoppable and still kicking at 92. So anyway, buy these books. I get £50 a year. Academic book publishing is a joke. You get maybe not 50, £500. Okay, that's not too bad. It's a tiny bit for school fees. So let me just, to finish up, something that is very close to my heart, which is this story of physical mathematics and why I got completely blown away, getting into this sort of stringy mathematics. And this is a field that I work on, which is called mirror symmetry. Just to give you a flavor of what string theory can do for mathematics, right? So to make it more precise. So let's go back first to Apollonius of Perga. So this is classic again, post-Euclid, Greek, antiquity dude. He asked a very simple question. So the question is, well, this one I know, given 2 points in a plane, how many lines can go through it? Well, 1, duh, right? And in fact, this is one of the 5 axioms of Euclid, of Euclid's geometry, right? So between 2 points, I can draw a line. That's fine, nothing crazy. But now let's just make it jazz it up, right? How many circles can I draw that's tangent to 3 circles? You can show that it's 1. And you can jazz that up even more. How many circles can I draw that passes through 1 point and then that's tangent to a line somewhere over here and cuts through another circle at some other points, right? Obviously this is generalizations of this this classical problem in geometry. Nothing crazy. Euclid would have asked himself questions like this. So if you think about things like parabolas, how many points does it take to fix a parabola? Well, the answer is 3. So if you just pick 3 points, you can always draw a parabola through them. So this is kind of a problem. This problem was formalized finally by Hilbert. Well, through a whole Schubert, there's a whole bunch of people, but it was finally formalized and posed properly by David Hilbert in 1901 in his famous address, where he raised the 23 standing problems in mathematics. And this problem is now known as enumerative geometry. Enumerative because we're counting how many things how many lines can you draw, how many circles can you draw, right? So Hilbert famously raised 23 most important problems at the turn of the 20th century, and these are called the Hilbert 23 problems. Hilbert 23 problems, and including things like the Riemann hypothesis, what's considered the most important problems to solve in mathematics. Number 15 on that list is to come up with a unified and axiomatic treatment of this problem in enumerative geometry. That started with Apollonius of Perga. Okay, it's still an open problem in terms of how to do it properly in full generality. Okay. Surprisingly, in 1991, Philip Candelas and Zene de Losa, who were my mentors in Oxford, found an extremely strange way to solve this problem for a huge class of enumerative geometric problems. You would never think that the problem to solve this problem, what did they do to solve this problem? They set up essentially a partition function in quantum field theory of strings, right? And they wrote down the partition function and did a Taylor expansion of that. And then when you do that Taylor expansion, you get integer coefficients which count this type of problem. I won't get into the details of this. You can ask experts here. I think Jan's sitting over there, you can ask him, and Ruth over there. Which is, these numbers count. These are huge numbers. They count what we call the number of rational curves on the quintic-Calabi-Yau threefold. Well, the technical details are not important. This is a branch of algebraic geometry. That's technical. But what is surprising is the technique with which they solved it. They solved this problem by constructing a pair of dual conformal field theories. They use string theory techniques to do it. And this completely blew the mathematics community away. They were just completely shocked, right? Just think about this. I have to solve a problem in Euclidean geometry, and the answer for a huge class of these problems is to construct a string theory and quantum field theory. What the hell? Right? What? I don't know why. It works. There's a long story about the background story to this as well. I can tell you that over drinks. So this is in 1991. Every algebraic geometer was convinced that string theory is correct, because you can't. How can the physics? This is the analogy would be like I solve a problem in differential equations in the 1700s, and they were like saying, oh well, Newtonian mechanics must be right because it's solving this problem about finding tangents of curves, and that the analogy is very much very strong in this sense. So this has led to Witten, who got the Fields Medal a few years after 1991. And this is a quote that you see. I'm putting dashes, physics or mathematics, because depending on different source, you see a different word here. But then again, I hope by this lecture I've convinced you that these two concepts themselves, these two disciplines, are themselves convergent. So just to wrap up. We're at the point. So here's a great book. It's called Quantum Fields and Strings: A Course for Mathematicians. This is a book that I grew up with as a graduate student, and the cover design is beautiful and great fun. Maybe it's not too clear, but what happens is, this is supposed to be the 1960s when physicists were studying things like Feynman diagrams, and mathematicians were thinking things like Chern classes and cobordisms and whatever. And things like this. And 50 years later, the blackboards are identical, except that the physicists are learning this, and the mathematicians are trying to figure out what a Feynman diagram is. And this kind of dialogue is exactly what's happening now. And then this picture, this cover of this book is really capturing the spirit of our times right now. And we're still doing this. And every day I love it because the only thing that I love more than doing mathematics is making new friends to do mathematics and theoretical physics. So I'm constantly talking to people in different fields and learning new things from them. What's better? So to now promise this is the end, the last slide. So I alluded to the difference between Plato and Aristotle. Oh, by the way, in medieval universities, all the ancient universities like Bologna, Paris, or Oxford and Cambridge, I think back in the day, the moment you enter the university, you have to declare yourself. You're writing with quill, probably with blood, that either you're Platonist or you're Aristotelian. And so, the Aristotelian world of physical observation and the Platonic world of pure mathematics in this sense. So I guess I've become a little bit of extremist, just a little bit, in the sense that I'm increasingly beginning to believe in this Neoplatonic idea that's been promoted by people like Max Tegmark, who said there is no physical reality, there is only mathematics, and physical reality is just a reflection of some underlying principle of mathematics. I'm inching towards such extreme, but that's a great analogy here because this allegory of Plato's allegory of the curve of the cave, where you see only reflections of this underlying thing, is mathematics is here and physics is here. Perhaps this is the right way to do it. And I can prove to this, at least I've convinced myself. You can go to this website and take this, which philosopher are you? And I'm not surprised that came out as like 70% Plato, so at least. And yeah, but I'm not 0% Aristotle. So you should all go to just take this QR code and take this test and see how much you believe what I've said today. So thank you very much.